A 3-ton chunk of metal is hurtling toward the moon right now at a blistering 5,400 miles per hour, and there is absolutely nothing we can do to stop it. While the lunar surface prepares to take a massive hit from an abandoned Falcon 9 stage, the grand plans for human spaceflight back here on Earth are facing explosive roadblocks. NASA's Artemis 3 mission is officially slipping, plagued by the harsh realities of deep space engineering, and SpaceX's Starship is wrestling with fiery pad-side aborts, proving how unforgiving innovation can be. Welcome to Astro Trivia, your front row seat to the most thrilling events in the cosmos. If you want to stay ahead of the curve on space exploration, gently tap that subscribe button to join our community. Now, let's dig into why our lunar backyard is about to get a brand new crater. Space is vast, but our immediate cosmic neighborhood is getting surprisingly crowded, and sometimes things go off script. On August 5th, an abandoned upper stage from a SpaceX Falcon 9 rocket is projected to slam directly into the lunar surface. But how exactly did a piece of a modern launch vehicle end up on a collision course with the moon? To understand this, we have to look back to early 2025. This particular Falcon 9 stage was tasked with delivering the Blue Ghost and Hakuto R landers. It did its job perfectly, deploying its payloads as planned. However, once its mission was complete, the upper stage was left stranded in what orbital mechanic experts call a chaotic, high-altitude cislunar orbit. According to Bill Gray, the astronomer behind the widely respected Project Pluto software that tracks near-Earth objects, this spent rocket booster has been tumbling in a highly unstable, lopsided trajectory for over a year. Caught in a relentless gravitational tug-of-war between the Earth, the Moon, and the Sun, the stage lacked the leftover propellant to either safely deorbit into Earth's atmosphere or escape into a permanent orbit around the Sun. The mathematics of this multi-body gravitational chaos eventually dictated only one outcome: a lunar impact. The 3-ton cylindrical structure will strike the far side of the moon near the Einstein crater at nearly 5,400 miles per hour. While this sounds like a catastrophic accident, for lunar scientists, it is actually an unexpected gift. When the rocket stage obliterates itself against the lunar regolith, it will carve out a fresh, artificial crater measuring dozens of feet across. This violent impact will excavate material from deep beneath the surface, throwing up a plume of debris. NASA's Lunar Reconnaissance Orbiter, along with other spacecraft currently circling the moon, will be eagerly waiting to photograph this freshly exposed subsurface material. It is a rare, free opportunity to study the geological composition of the moon without having to land a rover. But as lunar traffic increases, these accidental impacts serve as a stark warning about managing cislunar space debris. While the moon waits its impending collision, SpaceX is fighting its own fiery battles down in South Texas. The anticipation surrounding Starship Flight 12 is absolutely palpable, and for very good reason. This isn't just another incremental test flight. It marks the highly anticipated debut of the Block 3 generation. With Ship 39 and Booster 19 on the pad, this upgraded architecture brings humanity one massive step closer to the holy grail of deep space travel: reliable, in-orbit cryogenic refueling. The progress so far has been a complex mix of absolute triumph and frustrating physics. On the positive side, Ship 39 successfully roared to life at the Massey's test site, flawlessly nailing its 6-engine static fire campaign. But when it came to the Super Heavy booster, the narrative took a sudden, explosive turn. The 33-engine static fire test for Booster 19 was supposed to be a standard operational check. Instead, it became a dramatic lesson in extreme engineering. The test was abruptly cut short, triggering what engineers refer to as a pad-side abort. Why did it fail? It all comes down to the brutal reality of simulating hell on Earth. While individual components can be tested in isolation, firing 33 Raptor engines simultaneously unleashes an acoustic, thermal, and pressure environment that is nearly impossible to fully model on a computer. The sheer vibration and sound waves alone can tear metal apart. Shortly after engine ignition, a sensor located at one of the ramp manifolds in the launch pad's flame diverter system detected a sudden drop in pressure. Believing the infrastructure was failing, the automated safety protocols instantly commanded a rapid shutdown. This abrupt cutoff wasn't just a minor delay. Shutting down millions of pounds of thrust in a fraction of a second introduces catastrophic mechanical stress directly back into the engine turbopumps. As a result, SpaceX had to roll Booster 19 all the way back to the megabay, painstakingly removing multiple engines for meticulous inspection and replacement. It is a stark reminder that we are still writing the textbook on super heavy-lift rocketry. Meanwhile, infrastructure work is accelerating at Launch Pad 2, with teams aggressively testing the quick disconnect systems, pushing hard toward a full wet dress rehearsal. SpaceX is aiming for a thunderous launch later this May, provided the launch mount can finally withstand the unbridled fury of the Raptors. While SpaceX wrestles with the physics of a rapid launch cadence in Texas, NASA is facing a harsh reality check of its own in Washington. In a stunning, yet perhaps expected, update, NASA Administrator Jarrett Isaacman has officially confirmed that Artemis 3 is being pushed back to no earlier than late 2027. But the timeline delay isn't even the biggest bombshell. Under this newly revised mission architecture, Artemis 3 is no longer a lunar landing mission. Let that sink in for a moment. Instead of placing American boots back on the lunar surface, the mission has been fundamentally restructured into an Earth orbit rendezvous and docking test. NASA will still launch the Orion spacecraft atop the mighty Space Launch System, but rather than heading down to the lunar dust, Orion will perform critical docking operations with the commercial human landing systems right here in low Earth orbit. Why the sudden, massive pivot? It boils down to simple, undeniable physics and the incredibly complex technology required to keep humans alive in deep space. Both SpaceX, developing the Starship human landing system, and Blue Origin, building the Blue Moon lander, have bluntly informed the space agency that they simply need more time. The engineering hurdles are absolutely immense. We are talking about mastering in-orbit cryogenic refueling, the delicate art of transferring thousands of tons of super-chilled liquid oxygen and liquid methane between spacecraft while hurtling around the Earth at 17,000 miles per hour. That has never been done before at this scale. Combine that unprecedented challenge with the need to perfect long-duration life support systems that can reliably sustain a human crew for weeks in the harsh radiation environment of space, and the margin for error effectively drops to zero. NASA is making a highly calculated, risk-averse decision. They will not gamble astronaut lives on untested, unproven integrated systems. While this upcoming orbital test flight is a strictly necessary stepping stone to ensure the propulsion, communication, and life support architectures function seamlessly together before heading to the moon, it leaves a lingering, uncomfortable question. If Artemis 3 is now just a dress rehearsal in Earth's orbit, what does this mean for Artemis 4 landing, originally slated for 2028? The domino effect on the schedule is undeniable, and the dream of establishing a sustained, permanent human presence on the moon is proving to be far more difficult than the Apollo era ever made it look. But it isn't all delays and explosive setbacks. Let's shift our focus to a spectacular triumph. After an 18-month slumber, the absolute beast that is the Falcon Heavy has awakened. On April 29th, the triple-core heavy lifter thundered off the historic Launch Complex 39A at the Kennedy Space Center, violently tearing through the Florida sky. Its payload? the massive 6.5-ton Viasat-3 F3 communications satellite. The launch was a masterclass in aerospace engineering and orbital mechanics. 2.5 minutes into the flight, the twin side boosters cleanly separated and performed their mesmerizing synchronized aerial ballet, touching down flawlessly at landing zones 2 and 40. Meanwhile, to squeeze out every single ounce of performance required to push the heavy payload into a geostationary transfer orbit, the center core was intentionally expended, finding its final resting place in the depths of the Atlantic Ocean. This launch wasn't just a fiery spectacle, it was the critical final piece of a global puzzle. The Viasat-3 F3 satellite completes a highly advanced 3-satellite constellation designed to bathe the entire Asia-Pacific region, including vital remote oceanic aviation and maritime routes, in ultra-high-speed terabit-class internet connectivity. It is a striking reminder of how heavy-lift rockets are quietly, yet fundamentally, rewiring the infrastructure of our modern world from 300 miles up. Space exploration is an unforgiving arena where every milestone requires immense patience, fiery trials, and relentless engineering. From the chaotic orbits of lunar debris to the cautious delays of Artemis and the thundering return of the Falcon Heavy, history is unfolding right before our eyes. Thank you for exploring the cosmos with us here at Astro Trivia. Be sure to hit that like button, subscribe to the channel, and ring the notification bell so you never miss an update. Keep looking up.